Okay, I'm going to go ahead and do the 9.4 lesson on proofs. Start out with the launch. Go ahead and name all the congruent parts of the circle and explain how they're congruent. Well, I noticed that I have some parallel lines here, and so it's going to make arc AB congruent to arc CD, and that's because of the parallel lines intercepted arcs conjecture. Parallel lines intercepted arcs conjecture from chapter 9, and on your conjectures list should be number 85. You also notice that you have a perpendicular that goes through the center through a chord, and that's going to make BF congruent to FC, and that's because of the perpendicular to a chord conjecture. Perpendicular. And I can see that AG is congruent to GD. Since they're both radii. Which is also why GB would be congruent to GC. Looks like we have an isosceles triangle here. So that's going to make angle B congruent to angle C. That's because of it's called the isosceles triangle conjecture. So as the base angles of an isosceles triangle are congruent. So, and of course, angle BFG congruent to angle GFC, since they're both right angles. Okay, so that's our warm-up, and let's look at some different cases now. So sometimes proofs have to be broken into different situations and looked at one at a time. For the inscribed angle conjecture, there are three possibilities developing on where the center is in relation to the angle. And so in the first case, the center is on the angle. In the second case, the center is outside the angle. And in the third case, the center is inside the angle. So turn to the following pages and follow along with the proofs in case 1 and case 2, and highlight the portions of the diagram in the same color as the steps in the flowchart to help make sense of the proof. Then you will prove case 3. Some strategies you can use and add your own ideas as they arise is mark all the known right angles, mark all congruent radii, use congruent chords or arcs to mark congruent central angles or vice versa, and find congruent triangles with congruent radii, angles, or chords. So you're looking for observations based on the conjectures and definitions that you know. So case 1, let's go ahead and see what we're doing. We're looking at circle O with inscribed angle ABC on diameter BC. And we're trying to show that the measure of angle ABC is 1/2 the measure of arc AC. And so we'll notice how they start out with these being congruent because they're both radii. And that's going to make triangle AOB isosceles because the definition of an isosceles triangle. And separately here, we can see that we have an exterior angle Z, and Z is going to be equal to the sum of the remote interior angles, and X will equal Y because of the isosceles triangle conjecture, and that has to do with the base angles of an isosceles triangle being congruent. Then we can see how both of these are going to feed into this, where I substitute in X for Y, combine like terms, and then divide both sides by 2. And those are all properties of equality. And then notice how there's no arrows to number 6. So this is its own idea where x equals the measure of angle ABC. That's given in our diagram. And then z equals the measure of arc AC by the definition of arc measure. And so that's going to mean the measure of angle ABC equals 1/2 the measure of arc AC by substitution. And let's go ahead and look at case 2 now. So case 2 is looking at when circle O is outside the angle. And let's go ahead and prove that the measure of angle ABC is still equal to 1/2 the measure of arc AC. So in this proof, we're going to draw a line and right here, and then start out with saying that y is half the measure of arc dA, and then z is half the measure of arc DC. Because of the proof from case 1, we already proved that. And P plus Q equals the measure of arc DC by arc addition. And its own idea here, which is x plus y equals z, that's angle addition. And then we can do some substitution to say that y equals 1/2 P, because P is the same as arc dA. And so again, we can see lots of substitution being used here, more properties of equality, from just distribution to subtraction to substitution, and more substitution. So in these proofs, you're going to be doing lots of substitution using some of the conjectures from chapter 9. And that gets us then to inscribed angle case 3. So with this one, you're going to use case 1 again and more substitution. I'm not going to do it in this video. I'm going to do some different examples. So we'll move on from here back to the notes. So it says, now return to the launch and prove that triangle BFE is congruent to triangle CFE. So if we look at that, how would I prove that triangle BFG is congruent to triangle CFG? So how do I prove that these are the same? Well, you have a whole bunch of conjectures such as side, 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 or side, angle, side, angle, side, angle, side, angle, angle. All of these here work. And so let's just kind of pick one. Let's do side, angle, side right here. So if we were to do side, angle, side, we would first need to prove, go ahead and erase this here. We need to prove a side, so BG is congruent to GC, and then angle B is congruent to angle C, and then BF is congruent to FC. So you have a side, angle, and a side, and then by side, angle, side, the triangles would be congruent to each other. Okay, so put that down here. Let's go ahead and write it out actually. So BG is congruent to GC because they're both radii. Angle B is congruent to angle C because of the isosceles triangle conjecture. It says the base angles of an isosceles triangle are congruent. And BF is congruent to FC because, what did we say? Perpendicular to a chord conjecture. Okay. And so all of that's going to lead to the triangles being congruent to each other. Let's go ahead and do an example here of a proof. And at this proof, we're given, we have in a circle with an inscribed kite, ABCD, where AB is congruent to AD. So AB is congruent to D, and BC is congruent to CD. So from here, we're just going to start to make observations before we do this. I notice we have a kite. It's also a quadrilateral. And we do have a bunch of conjectures from the quadrilaterals chapter in the textbook. One of them says that angle B is congruent to angle D. It's called the kite angles conjecture. It says that the non-vertex angles of a kite are congruent. You also notice in chapter 9, there is a conjecture that has to do with cyclic quadrilaterals. So this is a cyclic quadrilateral because all the vertices are on the circle. And it says that opposite angles are supplementary. So angle B plus angle D equals 180 degrees. That's because of the cyclic quadrilateral conjecture that says opposite angles are supplementary. Okay. And we're trying to show that angle B and angle D are right angles, so that angle B equals 90 degrees and angle D equals 90 degrees. So it looks like we are ready to start our proof. Okay. I'll go ahead and get that going. Okay, so first of all, we're given a circle with inscribed kite ABCD, where AB is congruent to AD, BC is congruent to CD. And that's given. We also know that angle B is congruent to angle D by the kite angles conjecture. And we know that angle B plus angle D equals 180 degrees because of the cyclic quadrilaterals conjecture. So what we can do now is do substitution so that angle B plus angle B equals 180. Which means 2B equals 180, so B equals 90. And this would be combine like terms and divide by 2. And these are all properties of equality. Okay. So B equals 90, and that's going to mean that angle D will also equal 90 degrees because of substitution. Oh boy, I'll use a different color here so I can get away with this. Okay. And so that's going to mean that angle B and angle D are right angles. And that's the definition of right angles. And so in this proof, before we listed out what we observed, including the fact that it was a kite, that it was a cyclic quadrilateral. We looked back at conjectures about kites, and we found there was a kite angles conjecture that we could use. We also did some substitution, properties of equality, and we have our proof. Okay, go down here. In class, we looked at a few of these problems, and I'm going to go ahead and do number 1. And in class, we didn't get to number 2, so go ahead and give myself some more room to write here. Okay, if we make some observations before we get into writing this proof, what do we notice about it? Well, we can see that we have Cx is congruent to xd because those are both tangent lines. That's because of the tangent segment conjecture. So these here are both the same. And then xd is congruent to xa, the same conjecture. And since we have 2 equations, we're probably going to be using substitution to do our proof. So, looks like we are. Yep, we can see we have 2 tangent lines, we have 2 right angles, and we're trying to show that AB bisects CD at x, which means we're trying to show that CX is congruent to XD because the definition of bisect is to divide into 2 congruent parts. So let's go ahead and write a proof then. Okay, so we're given circles O and P are externally tangent with tangents CD and AB. Okay, and that is given. And from there, we know that CX is congruent to XD, and that XD is congruent to XA. And those are all by TS conjecture. With substitution, we can then assume that apparently I misspoke real quick. Hold on. This should say XA here. CX is congruent to XA. I need to slow down a little bit here. So CX is congruent to XA. XD congruent to XA. And since these are both congruent to XA, that's going to make CX congruent to XD. and that's by substitution. Which means then that AB bisects CD at X. And that's by the definition of bisect. Okay. Well, that concludes the video. If you need to see the solutions for the other proofs, they're in the Practice Your Skills solutions in OneNote, but that's going to conclude the 9.4 notes. The homework video will also go over some more proofs if you want more examples. Thank you. Have a good day.